In this video, we will be discussing and demonstrating how we can autoscale deployments using Kubernetes. But first, let's talk about why. In today's modern application landscape, requests may spike unpredictably, and there are cost effective ways to handle this, especially if you are using any cloud services. One way is to set up autoscaling for your cloud components to increase the number of servers in your cluster, depending on an increase in load. While this may work situationally, it's not always the best solution for dealing with scenarios where the load increases significantly, but only for a short period of a few minutes, as the cloud resources you provision may take some time to come up. During this time, the users may affect downtime or service unavailability. So, in scenarios like these, containerization is very relevant for modern applications as they allow us to scale up and down automatically within seconds, depending on load. Kubernetes handles autoscaling using a resource called horizontal pod autoscaler. It allows us to define custom thresholds based on which we can scale a deployment up or down within a cluster. The advantage of using this strategy for autoscaling is that it is quick and will work out of the box regardless of the cloud platform used, since it is a core Kubernetes component. Let's take a hands-on look at this demo, but first let's discuss the architecture and test scenarios performed. As a part of this demonstration, we have a 3-node Kubernetes cluster setup. In this setup, we have deployed an application which uses PHP and Nginx to connect to a PostgreSQL database, performing a simple select operation. This is to simulate a traditional three-tier architecture in a containerized format where PHP acts as the middleware. Under idle load, this application will have one pod replica running. We do not expect to see an increase in the number of pods. The request will flow from the client device to the web app service, to the web app pod, to the PostgreSQL database. The response will obviously flow back in the reverse direction. Under heavier load, once the resource requests cross our set threshold, the number of web app pods will automatically be scaled up to 2 or 3, depending on the amount of load on the cluster. The request flow will remain the same, the only difference being that the Kubernetes web app service will load balance traffic to the available web app pods based on the amount of resource on masters, the number of requests each pod is servicing, and a few other criteria. To test the scenario while implementing it in our demonstration, we are going to set up auto scaling to increase the number of application pods when they cross over 50% of their allotted CPU usage. So we will be setting up rules within Kubernetes such that each pod should only be allowed to consume a specific amount of CPU and memory. And when it crosses 50% of that allotted CPU usage, we will scale up. So we are going to test two scenarios. The first scenario is idle load. In this scenario, we are going to simulate 100 users making 10 requests each, and I have set up a ramp time of 10 seconds just in case my machine is not able to handle the sudden creation of new users. So we'll be having a total of 1000 requests by 100 users within 10 seconds. For testing our heavy load scenario, we are increasing the number of users from 100 to 1000. Everything else stays the same. So this should be a total of 10,000 requests by 100 users within 10 seconds. Now let's take a look at the demo. First, let's take a look at the components as part of this demo. So this is our PHP Nginx deployment, which connects to a PostgreSQL database and runs a simple select operation. As you can see here, we have a 50 millicore CPU resource request attached to it. Next is our services. Next is our PHP Nginx service. This is a node port service running on port 34957. Lastly, we have our horizontal pod autoscaler. As you can see here, we have configured our HPA to scale when the total CPU usage is over 50%. So out of the 50 millicore we have allotted, when the total usage increases over 25, we will be scaling up. So when the utilization is over 50, less than 50%, we will have one pod running. Between 50 to 100%, we will have two pods running. Above 100%, we will have three pods running. This is because we have set up the pod autoscaler such that there should always be at least one pod running, which is designated by the minimum replicas directive, and a maximum of three running regardless of the load. For viewing everything at once, I have split my screen into four sections. The first section shows the diagram we have referred to in our introduction for idle load. As you can see, it just has one pod for our one web app service. The second section shows the current CPU utilization via the metric server. The third section shows our JMeter test results. You'll see them when I'm running it. And the fourth section will show us the status of our HPA. Now let's try to simulate idle load to see things in action. We'll be using JMeter to simulate load to our cluster. And for idle load, we'll be simulating 100 users making 10 requests each to the cluster. So let's start with generating load. The metric server takes a little bit time to update. So while these things will happen in real time and all requests will be served, you'll see a slight delay in the updation of memory usage and the updation of status of the HPA. So as you can see here, 6 millicores are used. So the utilization has been 12% since our per core pod utilization is set to 50 millicore. So 6 millicore is around 12% of the allocated usage, and it has gone back down to zero. There has been no change in the number of replicas since we did not cross the 50% threshold. Now let's see what happens when we try to simulate higher load. For heavier load, we'll be simulating 1000 users making 10 requests each to the cluster. So let's go ahead with that. Okay, so as you can see, we have processed all 10,000 requests without any errors. Yeah, so the CPU utilization is 92 millicores, which is way above our thresholds. So since it is over 100%, our number of replicas is going to change from 1 to 3. And it will stay at 3 replicas for a short while. This is to make sure that if the spike in requests comes in bursts, if it comes every 1 minute or every 2 minutes, we don't keep creating and deleting pods, as that would be a waste of resources. So the way horizontal pod autoscaler works is it will create these 3 replicas and it will hold them even if the usage is at 0%. This is because it will be more efficient to hold than to keep creating and deleting pods whenever there will be a spike in resource utilization. So we can wait for a few minutes and this number of replicas should automatically scale down to just 1 because we are at 0% usage again. It has been a few minutes since we have no more increase in load, and as you can see here, the number of replicas has scaled down to 1. So this concludes our demonstration. For critical applications in your workloads, it would be prudent to set up horizontal pod autoscaler to handle spikes. Please be advised that CPU usage is not the only metric by which you may autoscale deployments in a cluster. You can also scale it via memory usage, network usage, requests per second, or in multi-container pods via container level metrics. You may also choose to use multiple metrics or custom metrics provided by the metric server. Thank you for watching. Hope this was helpful.